Thank you. Thank you. Yeah. Yeah. Thank you. Thank you very much. So I welcome you all for this workshop, one-day workshop on well test analysis using MS Excel. I'm Dr. Prince. I think I'm thanking Pragati to that she has given me a good introduction. Thank you, Pragati, and PA to make me to do number of courses in their organization. I'm always showing my gratitude towards them. And thank you very much. So let us start our topic, well test analysis using MS Excel. So today we are going to cover four things. One is inflow performance relationship, hydraulic fracturing, pressure buildup and drawdown, pressure derivative function. So these are the four things that we are going to cover. Quickly, let us start our first topic, that is inflow performance relationship, that too for oil wells. So what exactly is inflow performance? Shortcut, we can say it as IPR. IPR for oil wells. So IPR is unique. IPR will be different for different wells in a same reservoir. Like, if you are estimating IPR for different wells, it will be different. The values will be different. The parameters will be different, and the outcomes through IPR also will be different in the same reservoir. So what is the use of conducting IPR? Like why we have to estimate it? It will help you to give you information about the best stabilized flow rate for a particular well. So how it can able to justify that? Like, we are going to do a justification process. Like imagine if you are estimating certain parameters, see, every well will not be same. The projects will be different. The parameters, the challenges, whatever you face in the real time will be absolutely different. In the same reservoir, you have different IPRs. Like every well will be having different IPR. They are all unique. Probably the size of tubing of one well could not be suitable for other well. So maybe the production could be different. Like, if you provide an instruction with tubing size, choke pressure size, or whatever adjustments you have done in this well could not be suitable for the other well in the same reservoir, because of number of constraints that we may come across through the reservoir. Reservoir is heterogeneous. Most of the time we never know how it is going to give outcomes. That is what you are expecting. Like, you might have some methodology that will be followed, so you are expecting something to come in return, but it could not be the case. It may have different ways of understanding it, like the way how IPR will be different for one well to another well. So on the screen, what you are seeing is actually an ideal IPR curve. So this curve looks to be a linear curve, which is straight line, and y-axis is wellbore pressure and x-axis is flow rate. Just give me a time. I will open the laser. Yeah. You can see the x-axis is flow rate and y-axis represents wellbore pressure. So the axis starts from 0 to PR. PR represents reservoir pressure. That is the maximum pressure where wellbore pressure can reach. So beyond that, it will not go. Why? Because the pressure is equivalent to your formation pressure. So beyond that, there won't be any pressure measurement beyond PR. So, and the maximum flow rate for an IPR also will be given. And the name of this is, here it was written as Qmax, but there is another name. That is what we name it as AOFP, absolute open flow potential. So this is the best stabilized flow rate for a particular well, AOFP. So you're going to determine that AOFP. So absolute open flow potential. That is what it is here. And you can see that the IPR linear curve, which is intercepting on your x-axis. That means the y value of AOFP is 0. Why? Because it is intercepting on x-axis. And on the other side, the linear curve is intercepting on y-axis, where x value is represented to be 0. That means if your IPR is intercepting on x-axis, the wellbore pressures reaches to 0. That is the minimum pressure where you can get the maximum production. So when wellbore pressure is minimum or equivalent to 0, theoretically, it is not practically, we will not go with that kind of thing in real time. But the thing is, like, as per the theory, like if wellbore pressure comes close to zero, then the production of your well will be maximum. On the other side, when IPR is intercepting on y-axis, that means the x-axis is becoming zero. That means if the wellbore pressure is equal to the maximum pressure, which is equivalent to reservoir pressure, the production of your well will be zero. So when here there are two cases. When wellbore pressure means y-axis, it has two things. One is reaching zero, another one is reaching to the maximum. So once it is coming close to zero, when wellbore pressure comes close to zero, then the production will be maximum. When the wellbore pressure comes close to the maximum pressure, which is equivalent to reservoir pressure, then there won't be any production. Inside your reservoir, when there is a well, if it is drilled in a reservoir, it will be having drainage area. So beyond the drainage area, the pressure is equivalent to reservoir pressure. Near to wellbore, the pressure is wellbore pressure. Only the pressure difference make oil to flow from high pressure to low pressure. It's like diffusion from high pressure to low pressure. So the reservoir pressure should be high and the wellbore pressure should be lower. So lower means like a little lower will help you help a healthy way of producing oil, but drastic lower, maybe your well may not have that kind of capacity to exploit that kind of crude oil. Why? Because the volume is huge and tubing size is limited, so you cannot able to produce with that difference in real time. But in theoretically, if you see, when the wellbore pressure comes close to zero, the maximum production can be expected. But it is different from one well to another well, depends on its parameter sizing, tubing sizing, choke diameters, choke pressure, the kind of flow rate, the kind of reservoir permeability near to it. So many things are there which will impact IPR that we are going to see further. Before that, every well, ideally you have to construct an IPR. Why? Because if you have IPR of a well, then you can decide the best when you do any kind of adjustment, like if you are changing tubing size, if you're changing a flow rate or anything, that can be adjusted to your IPR to give you the best production. So this is the reason why we are going to measure IPR. Not only that, it will tell you, is there any impurities? Like imagine if plugging is there, if water saturation is more, or if gas is coming into your well in place of oil. So that also can be estimated through IPR. So first of all, let us try to understand with IPR, you can estimate another parameter, that is productivity index, which is represented as J. So you can see J is equal to QO by PR minus PW. QO is your flow rate by the pressure difference. We can say this as drawdown pressure, PR minus PW. PR represents reservoir pressure and PW represents wellbore pressure. So after that, QO is equal to, we can just adjust the equation in this way. QO is equal to J into PR minus PW. From this equation itself, it came. Imagine we have gone through two case studies, like AOFP means the maximum flow rate, that is Qmax. This is the condition, which is AOFP, where the y-axis, that is PW, when it becomes minimum, that means zero. If that is the case, you can give PW as zero over here, so that Q0 will become Q0 max, which is equivalent to AOFP. That can be simply written as J into PR. So this is how we can able to estimate simply the value. If you have the value of productivity index, then you can just cross multiply that with reservoir pressure. So reservoir pressure is not only that we have to estimate in this well testing, but you can get this through other technologies, like other data will be there, probably history data will be there, where reservoir pressure might already have been estimated. So you can use that data and cross multiply with productivity index to get the value of maximum flow rate. This is the maximum flow rate of that particular well, and that will be different for every well. And the graph, what I'm showing you is linear. That means there is no gas have been involved. This is for purely oil well. It is for incompressible fluid. If there is presence of gas, or if gas reservoir is there, then the curve will not be linear. It will be different. there will be some kind of, curvature will be there that has to be adjusted with logarithms. So this is absolutely linear. It is on linear scale. That means it doesn't represent any gas inside your reservoir. So in that way, simply we can say that the maximum flow rate, AOFP, can be determined by simply by J into PR. So how to determine how we can construct type? Very simple. You can do with two steps. Like one is single point test, another one is 2-point test. Imagine you have a well, allow it to produce at a two different flow rates. So if it is producing with some flow rate, there could be some pressure difference. If it is producing with another flow rate, that also have another pressure difference. So just two tests you have to do. If you have 2 points with two tests, you can construct IPR like this. So you have actually the values of one flow rate over here, another flow rate of here. So for this x-axis, which represents flow rate, you have corresponding y-axis, that is your pressure, wellbore pressure. So probably Q1 and P1, Q2 and P2. So you have two different flow rates. Only this is what exactly we need. Since it is linear, we need only 2 points. So one is Q1 P1, another one is Q2 P2. So right now, you have 2 points that you have installed on your XY axis. Then the next step is to connect both with a straight line. Simply just connect both with a straight line. First step is to connect both these two lines, then extend it these lines towards, like project it towards X and Y axis to get your reservoir pressure and AOF. It depends on the slope that we got it from these 2 points. So these 2 points will be connected with a straight line and you will be having a slope. With the help of the slope, you have to extend it on the Y axis as well as X axis to get reservoir pressure, the Y intercept, and AOFP, that is the maximum fluid Q max, that is on your X intercept. So when it comes to single point test, you need reservoir pressure. The data could be, you may get it from any other data if you already have reservoir pressure data. So that one you need. And if you have reservoir pressure, then there is no need to conduct 2 times a test. You can conduct even 1 time, that is enough. So 1 point is enough, where you can connect both these points and you can extend it towards your X axis to get your AOFP. So in this way, you can construct your IPR based on IPR. I will be showing you in the next slide. This is how the interpretation part of IPR will be. So you can see this graph, IPR, where the reservoir pressure, you can see on this set, the ideal graph of IPR is here, T1. Right now, I have shown you how to construct IPR, that is T1. So after some time, T1, T2, two different time scales. So if after some time, if you observe that here, there is some gap is there, and here also there is actually compared to this gap is even more. So why it is coming like that? What could be the reason behind that? So when time goes out, it should not be like this. So when how much it is being reduced, the same amount we can expect it also to be reduced here, but the reduction is more. So reservoir pressure is reducing here. This is what it shows. Y-axis intercept is reducing, means reservoir pressure is being reduced. Means the energy, drive mechanism that have been observed over there started to fade out. Because of that, the reservoir pressure started to get declined. Then here, AOFP is also reducing, like Qmax is also reducing, but not linearly. It is little bit more when it is compared to on y-axis intercept. That could be the reason of wax deposition or scaling effect because of paraffins and asphaltenes. So this is the observation that we can come to a conclusion. Like imagine if this is an observation, then we can think that there could be some scaling happening near by the perforations where it is not allowing oil to come freely into your reservoir. As well as reservoir pressure is also being reduced. That means drive mechanism energy is also becoming reduced. Actually, because of that only y-intercept is being reduced over here. And in the same way, when it comes to x-intercept, this is the reason. Like it could be because of asphaltene or paraffin scaling, if it is happening, because these are like we in our industry, like oil and gas, asphaltenes are not, paraffins are the least preferred one. So if paraffin scale is more, then the production will be constricted by it. So the flow will be reduced. So this could be one reason. When it comes to here, when both are reducing in a constant way, so this we can come to a conclusion at pseudo steady state flow, where the decline started without any effect. So declination means the overall reservoir energy started to fade out, but there is no other effect like scaling or water cut or any kind of effect. If it is not there, apart from reservoir energy that has been declined, so you will be seeing this kind of IPR, like when time one, it exactly the slope of time one and time two are same. If that is the case, we can come to a conclusion that we can conclude it in this way, like reservoir dry mechanisms energy is being fading out. Apart from that, there is no water cut or gas coning or any kind of other effects like scaling. We can avoid that kind of things actually. Then there is another kind of thing where the reservoir pressure was maintained. You can see there is no reduction at y-axis, but x-axis you can see it started to slowly get it. That means in place of oil, something is coming. What could be that? That could be water, which is near this. When reservoir pressure is maintained, means we can blindly think that it can be maintained only with water. Like, water drive mechanism can uh, create that pressure in such a way that the reservoir pressure will be maintained for some time. And mostly we can observe this at steady state flow. So during steady state flow, water drive mechanism will help reservoir pressure to be maintained. But even after that, x-axis is reducing. X-intercept is been reducing. That represents there could be water started to cone into your well. So water cut might have been, or water started to intrude into your well bore. So this could be only the reason where reservoir pressure was maintained and AOFP is reduced. This could be only the reason for water encroachment into your well bore. Then let us start to understand this in Excel. First of all, we have to construct IPR with the data that we have. So determination of oil inflow performance. Suppose two flow rates. If you have two flow rates, how to construct an IPR and get the value of reservoir pressure as well as AOFP. So we have the data test one, test two. So this is the flow rate for test one and test two, and this is the value for wellbore pressure, that is 2400 psi and 1800 psi. So 200 barrels per day and 400 barrels per day. So they have given a hint that gas to oil ratio are very small. That represents IPR will be linear. When there is no GOR, when there is no gas to oil saturation, IPR will become linear. If gas to oil ratio is more, means IPR cannot be linear. It will start to bend down. So that will start to have a curvature. So estimate the reservoir pressure and productivity index of a well and also determine the maximum flow rate. So that we are going to do with some more adjustments. So one is to find out reservoir pressure, and the same time we have to get the value of maximum flow rate, that is AOFP. And if you want to do some adjustment, like you are changing the diameter of tubing, so whether that is suitable to give best production, means that we have to estimate with this table. So you can see another table is there, three different flow rates at three different pressure drops. So this is also IPR data when you change tubing diameter. So without changing tubing diameter, this is the test that we have done, test one and test two. By changing tubing diameter, we have three tests, like three different flow rates with three different pressure drops. So how you can able to see, we have adjusted the tubing diameter and we have just randomly collected three different data. Right now, what we are going to do with that adjustment, what is the best flow rate that can be expected for that particular well with this adjustment? So that we are going to do, and more than that, we need to estimate the values of productivity index. We have ideal values over here. So I will try to, these are the modeled values. Then let us see in Excel whether the values what we are observing over here will come the same. So I'm going to share the Excel sheet. So is the Excel sheet visible to everyone?
Yes, sir.
Okay, thank you. So I kept already the value of IPR as well as the production data with the different tubing. The same table that I have shown you, I kept it over here. It's a simple data, only two tests. This is like 2-point test. So for that, first of all, we need to construct IPR. Then after that, we have to go for the next one. That is like we adjust the tubing diameter and we're going to see the best stabilized flow rate with that tubing diameter. So first of all, I'm selecting the x-axis, that is flow rate. And after that, I'm selecting y-axis, that is wellbore pressure. So I'm inserting a scatter plot. So this I got 2 points on your axis. So y-axis is your, I have to quickly adjust the values. That is y-axis is PW and x-axis, sorry, PW and x-axis is QO. We don't need this. Okay. I'm going to remove the grids, so it will be easier. And so right now, what I have to do is, first of all, I need to connect these 2 points. That can be possible by adding a trend line. So you just add a trend line that connects to both each other. So we can just adjust the trend line to look even more sharper like this. And so from here onwards, what we have to do is we need to project this trend line onto X and Y axis to get PW, sorry, PR and AOFP. So X axis intercept will be AOFP and Y axis intercept will be reservoir pressure, the way how we have discussed. So how to project it towards x-axis? Just to select the trend line, go to format trend line and go down, and for forward option is there. The units will be taken on your x-axis since you are going towards x-intercept. So 400, 450, the difference is 50. So you can start adjusting like 50. So it will start moving 50 units ahead. So you can see that projection has started to move forward. So in that way, we need more projection. So I will just type it around 200. So why? Because I need this trend will with the slope that it has created with the connection of those 2 points. So 200 is not enough. So I will go with 600. See right now, the value what I got it at AOFP, that is 1000. In the presentation that we have shown that the value what we got over there is also 1000. That is AOFP. So AOFP means the maximum flow rate can be estimated for this particular well is 1000 barrels per day. So this is AOFP, the way it is being connected to your x-axis, AOFP. Then let us start to see on the backward forecast. It's like the same thing only we have to do. So when it backward forecast is there, it will start projecting from here towards y-axis. I will start with 100. Can make it around 300. So it started to intercept at 3000. So you can see that it is actually intercepting at 3000. It may not be 300. So 200 could be the one which is a suitable. Yeah, 200. So this is AOFP, how we have adjusted. And we can name this as PR, reservoir pressure. So the value of reservoir pressure where it is intercepting on your y-axis is reservoir pressure is the intercept of IPR on your y-axis. The intercept of IPR on x-axis is AOFP. So the value of PR is 3000. The value of PR over here is 3000. And the value of AOFP is coming around 1000. So we can, from the value of this, we can estimate the value of productivity index. And we know in the presentation, I already told you what is the value of A over FP theoretically? J into PR. So what is the, how to estimate the value of J? This is the formula, Q naught by PR minus PW. Let us try to estimate the value of QR by PR minus PW. So that means I'm estimating productivity index. So Q naught, so the value is 2,200 barrels by PR minus PW. PR minus PW. Corresponding to two different pressures, you got the value. So here the value is 0.33, but here since the value I haven't given anything there, so both the PRs are same. Both productivity indexes were observed to be same. What is that I have done is nothing. I have just kept the value of Q naught for this by PR, which is represents PR is the one which is representing 3000 minus PW, corresponding pressure to that particular point. In the same way, when it comes to the second point, it is taking Q as 400 and PW as 1800. And we got productivity index for 2 points same. That represents the slope is equal for the 2 points. Like IPR slope is same wherever you measure. So that is one thing. So right now we have gone with production data, like we have adjusted the tubing diameter and we got these 3 points. So right now, what is my objective is to estimate the value of best stabilized production for that particular adjustment. So for that, what I have to do? This is my tubing diameter. So I'm going to insert a scatter plot for this. Insert scatter plot. So you can see the scatter plot is looking to be 3 different points. I'm going to remove the grid blocks, but I want to know these scatter points has to interpolate on IPR to get the best stabilized flow rate. I would like to show you the presentation once again to make it confirm. You can see these points were plotted on the IPR and the intercepted point have been projected towards your x-axis to get the best stabilized flow rate for that adjustment. So that we are going to do right now. So here, how to interpolate this on IPR? So this is the question that we have to come across. So I cannot actually, do that directly. Even axis is different. You can see the axis minimum value is 0 over here and the maximum value is 3,500. First, I will adjust that. So y-axis minimum value, I am putting it, minimum value, I'm putting it as 0. And x-axis minimum value, I am putting it at 3,500, which is equivalent to your IPR curve. When it comes to x-axis also, the minimum value is 0 and maximum value is 1200. So I'm going to adjust the value of x-axis to 0, which is already there, and 1200. So this is what my graph looks to be. And I have to skew this graph in such a way that it fits exactly the way how my earlier graph fits. So this is my earlier graph. This is my adjustment tubing diameter graph. So right now what I have to do is I need to add the trend line. So trend line, simply we can add it like this. I am just putting it a red line so that it will be different from IPR. So right now I need to put it on it, but I cannot see directly. So what I have to do is I need to minimize the area which is showing to be the background area has to be reduced, means it has to be transparent in such a way that we can understand what is happening at the other side. So for that, I am just adjusting the format chart area and I am trying to keep it transparent, not like this, fill solid line in that. I'm just trying to make it transparent. So you can see, I just faded out the background area and I'm trying to adjust the axis in such a way that both axes will become same. So you can see that the both axes are observed. I'm trying to adjust the both axes, which will come to the same. See 400 600. In the same way, we have to adjust. This is what manually we have to do it. So all the values should exactly match. Almost 90% is it was over. So we have to just concentrate on matching the axis. Yes, I think we can come across. Certain points are little fading out, no issue. Yes, this could be the exact fit. It may not be 100%, but exact fit. So you can see all the x-axis values and y-axis values are one on another. So right now, this line is intercepting over here. So what I will do is I will be adjusting the value. I mean, I will be taking the value from the intercepting point where exactly it was intercepted. I will try to draw a straight line. So in this shape, this acts like a scale. So exactly this is the point where it is intercepting on your x-axis. Comes close to 400, like 400, maybe in between it is 500. Probably you can take it as 450. So I will just write the value over here. So 450 is the best stabilized flow rate. This is related to Q, which is connected with your adjustment of tubing diameter. If you have adjusted tubing diameter, then we will be getting another IPR. That is what this is. And you are plotting this IPR on your original IPR. Like every well will be having an ideal IPR that cannot be changed. But if you adjust anything, the IPR will alter. So when you are cross-plotting that on your main IPR, you have to take that intersection point and project it towards your x-axis. So that is your flow rate. And right now, the best flow rate is not AOFP, but the best flow rate for that adjustment is 450. But IPR flow rate AOFP is 1000. But when you adjust your tubing diameter, then the best stabilized flow rate can be expected at 450 barrels per day. So this is the reason IPR will help you to give you the best outcomes of your adjustment. Like you can adjust, so it can be done with any kind of adjustment. Wellhead pressure can be adjusted, chokes can be adjusted, choke pressure can be adjusted, choke diameter can be adjusted, even tubing diameter, tubing pressure, any kind of adjustment you have to cross check with IPR. You have to plot it on the IPR and you have to get that interception, and finally you have to project it on your x-axis to get the best stabilized flow rate for that particular adjustment. So this is the reason why IPR is taken as very good parameter to be considered for the best production. So right now you can see this is what exactly I have done. I have extrapolated this IPR, which was represented as TPR, tubing performance relation. Why? Because we adjusted related to tubing. So since tubing, we are trying to observe that kind of tubing adjustment, what will be the outcome? That is how exactly we are determining. So we are just taking IPR after tubing adjustment, and we are extrapolating on IPR, and we are seeking for the interception, and we are projecting from that interception towards your x-axis to get the best flow rate for that particular adjustment. So this is the one. This is what exactly I have done. So this is what exactly manually it will be done. Right now we have done with Excel. Then comes the next one, that is back pressure test, that we will be discussing in gas well testing. So IPR x-axis, y-axis are different, and this gas well testing, this is also an IPR. If you could observe over here, what you are seeing on the screen is also an IPR, but you can name it as GPR. GPR means gas performance relation. Right now I have told you what is TPR, that is tubing performance relation. So currently we are with GPR, that is gas performance relation. But this cannot be done like oil well. So this is different. So for that, y-axis is not just about PW, but this is the difference between squares of pressures, reservoir pressure and wellbore pressure. So you need to take the difference between square of reservoir pressure and wellbore pressure. That is your y-axis. And on x-axis is flow rate of gas, not oil. So that is flow rate, that is small q, which is related to flow rate of gas. Why? Because this is purely gas well. There is no oil is present inside the reservoir. Then right now, earlier for oil IPR, we took 2 points, but for gas IPR, we need 4 points. So you can observe here, 1, 2, 3, 4. So we need 4 different tests has to be conducted to estimate the value of GPR. Here also we are estimating AOFP. Means in a gas well, what is the best flow rate? That is AOFP. And reservoir pressure will be here. So you can see AOFP have been measured at y-axis, that becomes 0. That is the minimum one. So that is your first case. When y-axis become maximum, you will be getting reservoir pressure. But this pressure value you will get in square, that you have to make it like you have to square root it to avoid the square to get the main reservoir pressure value. So first of all, we need to estimate the value of AOFP by using back pressure test. So how you are going to conduct this back pressure test? For that, we need 4 points. 4 tests has to be conducted. So we need 4 points. For oil IPR, we need only 2. But for gas, we need 4. And you can observe this is how the graph looks to be, that we will be quickly going into Excel and we will be doing it. And this is the equation, ideal equation to consider. Why? Because this is also a linear graph. Why it is linear? Why? Because we are squaring it and we are actually, this graph is log graph, not semi-log, it is log. Both x-axis is in logarithm, y-axis is also in logarithm. Not only that, we have done square difference on your y-axis. So this is the difference between oil IPR and gas IPR. One y-axis will be different. Then it is not linear coordinate graph, it is log graph. So x-axis will be in logarithm, y-axis also will be in log. After doing all these alterations, you will be getting a linear straight line, which will have a linear slope. So let us try to estimate. We are converting that data into a linear plot so that we can able to estimate the value of AOFP easily. So that is one is QSC, that is which represents flow rate of gas at standard condition, is equal to C and both are constant that we are supposed to estimate. PR represents reservoir pressure, PW represents wellbore pressure. Okay, for maximum flow rate AOFP, C into PR square power N, since PWF is equal to 0. We already discussed earlier. For AOFP, PW will be 0. Here also AOFP, PW will be 0. The same concept will continue here also. But before that, you need to estimate the value of C and N. If you know these two values, you can start constructing other points. If you have 4 points, you can start constructing even more points. And finally, you will reach towards a point where the pressure will be the minimum, the corresponding to that, the flow rate will be the maximum. So that is what you have to do. So first of all, they have given the formulas for C as well as N. C is equal to QSC by PR square minus PW square power N. And 1 by N value was also given. This is actually inverse of a slope, 1 by N. So log of your y-axis second point minus log of your y-axis first point by log of your x-axis second point minus log of your x-axis first point. So let us get into the data that we have, and these are the different tests that we have to conduct. Back pressure equation, that is the one which we are doing right now. So this is the equation, QG is equal to C into PR square minus PW square power N. And there are other tests also there. So these all tests will help you to get like pressure square equation, pressure equation, pseudo pressure equation. So these all tests also will give you the value of AOFP. But currently we are doing back pressure equation. So let us start quickly going to Excel. So on the screen, what you are observing, I kept the ideal graph over here, this side. So this is what I'm going to generate right now. So you can see the graph. So y-axis is PR square minus PW square, and x-axis is flow rate of gas, and x-axis is in logarithms, y-axis is also in logs. So log graph, and we need 4 points that I am going to show you over here. So we have 4 points starting with 0, and we have another flow rate. For that, this is the pressure, another flow rate, that is the pressure, flow rate, that is third point, we have pressure. So we have actually 4 different points. So based on this, we need to construct this equation. And moreover, we need to get the value of AOFP. For that, first of all, what we need is AOFP is the condition where PW is equal to 0. So you can see here PWF, it is reducing 1952, 1700, 1500, and 13,000. So like that, it is started to get reduced. And if Excel itself has an iteration, by based on that, if you start projecting it, I want 0. So I can see that the values are reducing, and finally I reached a minus value. I don't want minus. I just want up to the minimum value, that is 200. These are all projected values. These are all given values. These are all my projected values. Then finally, after 211.6, I am getting -4. So which I don't want. I want only 0. These are actually, I'm taking some random values in between 0 and 1952. You can take here as 1000, simply like that also, like 1000 you can take, then 600, any projected values like 600, 500, any ways like that you can take, like 400 and 200, and finally with the difference I'm getting finally 0. So I need to know the value of flow rate corresponding to this value. That is it. That is my AOFP. So right now, what I have to do, what is that I have to go to get that value? AOFP can also be given as C into PR square power N. So that also I can take it as C like this. AOFP can be simply given as C into PR square power N. If I know the value of C, if I know the value of N, I can get the value of AOFP. Since the pressure squares also will be observed, first of all, we will estimate that also. Before that, let us try to get the value of 1 by N, N and C. So C is QSC by PR square minus PW square power N. So if you want to get the value of C, you need to know the value of N. So that means first of all, we need to get the value of 1 by N. Log of PR square minus PW square 2 means log of, let us take y-axis as PR square minus PW square. So here what I have taken as 1952 is your highest pressure that can, where the Q max was observed to be 0, that will be your reservoir pressure. So the reservoir pressure, that is PR square, that is 1952 square, or else I will just solve it once again. So I am taking this as reservoir pressure, that is equal to this square minus, for first point, the same value only will come, square. Okay, so I have to equate it. I got the y. Why? Because 1952 square minus 1952 square, it will be 0. Right now, what I will do is, I want to see PR square is constant in the formula. PR square is constant, but PW square only will change according to the table. So for that, I am making this as function F4. So I am keeping that as constant. So that will be 0. But when I start moving down, I got these values. So this is my PR square minus PW1 square, PR square minus PW2 square, PR square minus PW3 square. Like that, I got all the values. Since I have other values of these are my real-time values. So I will calculate. These are the projected values. I will just change the color of it so that it will not be confused. So these are the values which were projected down to get the value of AOFA. I kept it. So right now I'm going to go with the available data. So the data up to now what I generated is from the data what I have. PWF value I have. So PR square minus PW square I have calculated for all the 4 points. Then I am going to calculate 1 by N. Log PR square minus PW for second point, like Y2 minus Y1 by X2 minus X1. So for that, what I will do is log y2 minus y1. I select any of these 2 points. We have 3 points. I'm selecting 2 points. You can take even first and last point also, first and second point, or third and fourth point, anything. But I am taking just 2 points next to the first one, since the first one is 0. So I'm taking the one which is next to it as well as corresponding to that one. So log y2. So right now my y-axis on the graph is PR square minus PW square. I will start with a bracket log y2. So my second point is this minus log y1, that is this. I have closed the bracket. So my numerator part was completed, and denominator when it comes, then that will be log q values. That is my x2 minus log x1 value. That is this. So I have completed the denominator part, and I'm going to equate it. So the value of 1 by n is 1.14. So inverse of it, 1 by this value give me my n value, that is 0.87. So you have the value of n. You can take any point over here to get the value of c. Okay, so let me check out the value of c. So you can take any point. I will take the second point, QSC. Corresponding to that, my y-axis value, that is PR square minus PW square, power n value. So I got the value of C also. So I have the value of C, I have the value of N, and I have the value of PR as 1952. I will simply put PR value as 1952. So you can get the value of AOFP here simply by C into PR square, since PW is equal to 0. But I'm going to generate, since I have an ideal equation for back pressure test, I will check out whether the generated values will give me the values of QSC by using these two values and this pressure value. So if that is the case, my projections are right. So for that, C into PR square minus PW square, that is this, power n. So first value is the same, and let me check out with other values. No, why? Because these values I have to block it. So C value is constant, function F4, and n value is also constant, function F4. Then from that, if I project it down, I am getting the value. You can observe the values of this as well as the values of this are same. So the projected values are same. I can reduce the size of it. Decimal size I have to, you can see 2625, 2625. This is my modeled equation where it has generated data of this. So right now, what I can get benefit from this is, I have data up to here with the pressure drop up to 1300. If I have even more drop, like 1000, I don't know, I don't have the real data, but from this modeled data, I can start projecting it down. So I already have the value of 1000, 600, 500, 400, 200, and finally 0. So I want to know the value of flow rate when the pressure is equal to 0. So that is my AOFP. So from here up to here, I reach. So for that, if I go forward, it will ask me the value of PR square minus PW square, since there is no projection over here. So if I have projection here, then I will get the projection over. For that, what I will do is, since I have this value, I will start forecasting it forward. So I got the values. So PR square for 1000 minus 1952. In the same way for 600, for 500, and this is my AOFP value, where the value is PR square, that is 0. I'm sorry, PW square is 0 and PR square is as it is. So since I have these y-axis values, I will be exploiting it, projecting it down. So this is the value where I am 9,034. 9,034 cubic feet per day is the best flow rate or maximum flow rate for that particular IPR. That means the value of 9,004, I will just make it like this. This is actually this. This is the value. Why? Because this is the point where y-axis is 0, minimum, PR square, that is this one. So this is how we can able to estimate the value of AOFP and for gas wells. So this is one way of getting it, but there are other equations are also there that will help you to get the value of AOFP. So there are more things has to be done. This is actually the linear most one, and other things will come with other kind of differentiation and other things are there that has to be considered. Up to here, everyone is okay. Like are you following through this? I need one hint. Thank you. I will go ahead. So hydraulic fracturing is another important technique. Mostly this will be done for shale reservoirs, since they are tight. What is the concept of hydraulic fracturing? Like, we are going to inject fluids, hydraulic fracturing fluids into the reservoir formation to create fractures. So once a fracture is generated, the flow will start to come automatically into your wellbore. So generally, tight formations, the flow movement will be very less. But if you generate a fracture, then the flow will start to be more easier, smoother, so that it will start to enter into your wellbore. So you can see over here, I will just zoom the diagram. So you can see that hydraulic fluid, this is the wellbore, and it started to generate fractures into these perforations. So you can see this is the point where exactly they're zooming. So you can see how the fractures and fisheries that have been generated over here. In this hydraulic fluid, it carries some sand particles as well as water. So it is mixture of some part of sand, water, and other chemicals. So that this sand particle acts like some kind of barriers to hold the fracture. So it is not that once the fluid enters, the fracture will be generated. When the fluid is removed, the fracture will be closed. That is not the case. So once after the fluid have been removed, the fracture should stay static, or else the fluid may not start to enter into your wellbore. So in that way, first of all, what we have to do is, like, these sand particles will act like a barrier to hold the fracture from top side as well as bottom side, so that the fluid will start to enter into your wellbore smoothly. Okay, so this is how it will be generated. I will just show you a small animation to how this will happen. So first of all, this is the wellbore, and fracture have been, perforations have been generated over here. So it will create a channel. So initially, perforations will start with a channel, so that you can start injecting your hydraulic fracturing fluids. Like, the fluids will start to enter with sand particles. It will be entering into the reservoir. So after some time of injection, a fracture will be generated. A bigger size fracture will be generated, where the fluid will start to continuously enter into your. So that what will happen is, all the sand particles and chemicals will enter into your fracture. Once this injection was stopped, that will be holding it. That volume of the fracture will be holding static, so that the fluids from the reservoir will enter smoothly into the volume, and it will start entering into your wellbore. So that also has a limit. Why? Because these sand particles also have a limit for some time. Then after that, it will collapse. Then the fracture will be totally collapsed. Once the fracture collapsed, all the formation fluids which were present will be bleeded into the formation. Then the production will be as it is. This will help you to increase the production in less time. Since you are increasing the volume of channel through a fracture, the much amount of reservoir fluids will start entering into your fluid so that you can collect more amount of oil. And this is mostly used for tight reservoirs as well as for shale reservoirs. Today, shale technology is booming a lot. Like most of the projects, they were paying a lot of attention towards shale reservoirs, where hydraulic fracturing is acting as a very good technology for them to exploit good amount of crude oil through shale formation. So this is the helpful technique. Currently, USA is going through shale reservoirs a lot. So it is a very good technique for shale as well as tight reservoirs. So for that, this is one test is the formation integrity test. So if you conduct a test, you will be observing a graph which looks to be like this. When you are injecting fluid, the pressure will start to rise up. Once, if you observe the slope is deviating, means there is a leak of pressure. That is the point what we will be mentioning when the slope is changing from one angle to another angle. That means the initiation of fracture have begun. The point where the slope have been altered, that point we name it as LOP, that is leak of pressure. So where the slope will be deviated. So once the deviation happens, then the fracture volume will start to increase while accepting the fluid into it. So in that way, the pressure will start to deviate, and finally it will reach towards a position where fracture will burst. Like, like the channel will burst into a fracture. So once that huge volume have been generated, then the flow of fluids like hydraulic fluids will very smoothly, and with it requires more volume of fluids to enter inside to maintain the pressure. So the pressure will immediately drop. Why? Because the volume is big. According to Boyle's law, volume is big, pressure will be reduced. So here the pressure starts to get reduced. Why? Because the volume of channel have increased through generating a fracture. So once after certain period, all the hydraulic fluids which you have injected will occupy into the whole volume of your fracture, and that also, then after that the pressure will be showing to be maintained in a constant way. That means the fracture is holding the hydraulic fluids. So that is what we say it as FPP, fracture propagating pressure. Means fracture is maintained by injecting hydraulic fluids. See, you are holding something by putting a liquid. Since the hydraulic fluids are water, which is incompressible, where the fracture cannot compress it, so that it is been holded by injecting fracturing fluids, that is water, sand, and chemicals. So the sand particles, which after that, what we are supposed to do is, like, we have to stop injecting. Means the fluids were not injected into the fracture. Right now, the sand particles which were present inside the fracture will hold the fracture. That those sand particles which were inside hydraulic fracturing fluids were there, which were present inside the fracture, will hold that fracture to maintain that volume. So that also will continue for some time. So when you stop injecting, then sand particles will act like a propellant. So that phase we will be starting at ISIP. So ISIP means initial shut-in pressure. So shut-in means you are not injecting hydraulic fracturing fluids. So you stopped injecting hydraulic fracturing fluids. Even after that, the volume of fracture will be maintained as it is. So since it is maintaining as it, how it is been maintained like that? That will happen only with sand particles which were injected through hydraulic fracturing fluids. So that phase also will continue until you reach the final phase, that is fracture closure pressure. So at that particular point, the movement of sand particles also will be, the propellant acting of sand particles also will reduce, and finally the fracture will close. Once the fracture closes, it will just bleed all its formation fluids into the formation. So whole the fracture will start to get collapsed. So this happens at initial time. So if you continue to do this cycle for number of times, like 6 times, 7 times like that, then even after without injecting fracturing fluids, the fracture volume will be maintained for longer period. So that is what exactly we need. Why? Because more time the fracture is in its form, you will be getting much amount of oil. You can see over here the same thing what I was talking about. So from here to here, this is the line I'm talking about. Here this is less and here it is more. So the reason is we need that from initial shut-in period to fracture closure period, that gap should be more. Means the pressure maintenance should be more. Means that is the volume of fracture which was maintained over there is more. So because of that, more amount of oil can be collected with more amount of time. Here time consumes. If more time consumes, more amount of oil will start entering into your production. If less time fracture is there, means less amount of oil can be collected. So if you see in real time, like let us observe in the real time data so that you will be having an idea of it. So this is the injection time, like time 0, 5 hours, 10 hours, 15 hours, and injection pressure. So this is the pressure data that we have. So you can see the pressure data, all this. So right now what I'm going to do is I'm going to just show you the points I have mentioned right now. So you can see a graph. This is formation integrity test, FIT. So you can see that the pressure is been reducing while you're injecting fluids. Then here onwards, the slope have changed. How to know that the slope have changed actually? So just to try to connect all the points with a scale, then we will be knowing it. So here you can see this is how the slope is been increasing. I'll just change the color of it. See, this is the slope for the points which they were it was being hidden inside the line. That means all the points are touching the straight line. So after that, certain points have gone deviated from the straight line. So that is the slope. That is the change of slope. Like, you know, that is what that slope is different. So this is what I'm talking about. So this is the point where exactly slope have changed. So this point we name it as LOP, leak of pressure. Leak of pressure. After that, it started to move down. Like I will just try to adjust with an outline. So you can see that it started to move down. So that means here the fracture have reached to the maximum. Right now it has bursted. Like, you know, the channel have become into a fracture. Like it has increased its volume. The point where exactly the you know, like where the fracture have generated, that we name it as FBP, that is fracture breakdown pressure, FBP. So this is the point, the maximum pressure it has reached, so that the channel have breakdown to a fracture. So that is fracture breakdown pressure. Then after that, the fluids have started to enter inside, but pressure is been reduced. Why? Because volume have increased. So once after reaching to a particular point, then the pressure was observed to be in a constant way. So that can be taken as like the point where it started to reach constant, that we can make it as FPP, fracture propagating pressure. So the fracture started to maintain itself. Then after that, it has reached to a position, then you stopped injecting hydraulic fracturing fluids into the formation. So that is when you stop injecting, that phase we name it as shut-in period. So initial shut-in started over here. So ISIP, initial shut-in pressure. From here, you can see the maintenance of fracture is very less. Like, you know, little bit time, not much time, probably few hours it has maintained. Then finally, it ended with fracture closure pressure. So once it reaches fracture closure pressure, then the fracture will collapse. So the fracture started to collapse from here and the pressure started to drop down. Again, you repeated the same test, but hereafter, this time, second initial shut-in pressure to fracture closure pressure, you have a bit better gap actually. See, this is the point where second time it reached. There is no FBP here. Fracture reopening pressure only will be there. Since it's already created a fracture, there won't be leak of pressure. Directly it will open once again. So that is the reason it is not reaching to that level of pressure. Why? Because already that fracture have experienced earlier. So that again, if you start doing it once again, then it will start directly creating a fracture very smoothly. So it will not take much time. So from ISIP to FCP, see the difference for the second test. You can see the difference over here. So ISIP to FCP. So here the time period is less, but here the time period is more. Means like the fracture maintenance is very high. Like the time period it has taken to close the fracture is more, means that it is producing good amount of reservoir fluids into your wellbore. So the time is more, means more amount of oil have been produced into your wellbore. So this is the reason a formation integrity test will help you to create a fracture. Not only that, if you do it cyclically for more times, like 7 or 8 times, the carrying of that fracture will be for more time. That means the production of oil is also more. So this is actually a stimulation technique that will be mostly done for shale reservoirs or tight reservoirs like carbonate reservoirs. So where the formations are tighter, so you are creating a fracture. It is not that suitable for sand reservoir, but mostly it is suitable for tight reservoirs where crude oil, the flow of crude oil happens through fractures. So fracture is a suitable technique over there. So because of that, this test will be conducted to get the best output of oil by generating that volume of fracture over there. So this is the purpose of conducting formation integrity test. Then let us go with the presentation, and after this, pressure drawdown test. So this is also a familiar technique that we will be doing in well testing to estimate number of reservoir parameters. It is one of the most profound technique that will be done to rely on the confidence level that it produces in different parameter areas. So you can observe, like initially pressure drawdown test means, first of all, you need to allow the well to shut in. So during shut-in period, the flow rate will not be there. So there is no flow rate during shut-in period. Why? Because you're just closing the well. So in that way, the wellbore pressure will reach to its maximum position. You can observe the laser was kept that it has reached to the maximum, which is equivalent to reservoir pressure. Then you allow the well to produce so that the pressure will start to drop. In the same way, it started to produce with positive production. So that is positive flow rate. So the flow rate will be positive and the pressure will start to get reduced. But when you do this, this also will be done cyclically, like pressure drawdown, build up, like that. Continuously, it will be done for 4 or 5 times to get that kind of stimulation so that the production will be maximum. So initially, you will get some information about wellbore, what is happening around your wellbore. So first of all, you will be seeing this is how the graph looks to be. So it will be deviated from the main points. So whatever we observe, so this is like the points that started to deviate from your main slope. Then after that, it attains the slope, normal slope. Then again, the deviation will start at the end of it. So the end deviation can be considered that you reach to end of reservoir drive energy, so that the point started to fade out. That is considered as pseudo steady state flow. But at initial phase, the deviation happens because of wellbore damage and skin effect. So wellbore damage, skin effect. Both are two different terminologies. So both will be considered as damage around your wellbore. Like this is for damageable thing that we are supposed to estimate. So wellbore is internal, skin is external. So skin means the damage around your well is considered as skin effect. The damage inside the well is considered as wellbore damage effect. What is wellbore damage effect? Probably you might have used some drilling fluids, workover operation chemicals, to continuously do it to complete your well, like open hole completion, cased hole completion. Finally, you have completed your well by doing all these operations, workover operations. So these chemicals and other things which will be inside your well, sometimes it might be inside your annulus that will fall into your wellbore horizon, like where exactly oil will start to enter into your wellbore, that near to perforations. So once it falls there, it will mix with oil and it will start producing with oil into your wellbore. So because of that, we don't need these kind of fluids at the surface. We need to separate that from the oil. So it shows that as if we are producing good amount of oil, like the normal one will be there, normal amount will be having some pressure readings. But because of this unnecessary chemicals and other things mixing with oil, it generates more, uh, you know, uh, more pressure, unnecessary. Like you can see the pressure was up on the upper side. That represents you are getting good, more amount of oil than it is required. So that means it shows that something more it is coming with the oil. What is that additional oil that we are getting is nothing but the workover chemicals that were present in the annulus inside the wellbore. That will start to mix with your oil and it will start producing initially for some time. So the wellbore damage effect will take for some time. After that, it will fade out. Once it started to get reduced, then you will start, these points will lie on the main slope. Then after that, the production will continue. And finally, the reservoir dry mechanisms energy will start to, like primary recovery will be reduced. The energy will fade out. Then the production will start to decline. So this is the declination phase where we can consider that as pseudo steady state phase. That is about drawdown test. So when it comes to how to estimate permeability, so we need to have the data as wellbore pressure and uh, time, which corresponds to, we need two times here. One is shut-in time, that is delta T, and production time, that is TP. So here TP is constant, delta T is a variable. So delta T will be changing with respect to TP, and we are going to estimate TP plus delta T by delta T, and it is a semi-log. X-axis is log, y-axis is linear one. So if you have this data and you have to observe the slope which is following the main slope, not the slope which have been deviated, with the help of slope and other parameters, you can get the value of permeability. This is for drawdown test. Then when it comes to build-up test, this is how the build-up pressure, the same thing like how drawdown have done. Next to that will be carried as build-up. Like, initially the well will be uh, allowed to flow for some time, that where you will be measuring some parameters. After that, you will be shutting the well. During shut-in period, the pressure will start to build up. So this is how the pressure started to build up. So while building this pressure, also you can estimate some parameters. So with drawdown and build up, you will be getting more information. So drawdown, next to that, cyclically, we will follow with build up. So early time, middle time region, and late time region. So in these time regions, if you have skin effect, wellbore damage effect, and you can estimate the permeability around your wellbore, you can estimate the permeability inside the skin zone. So whatever parameters that can be extracted by wellbore and pressure drawdown and buildup, that can be extracted at initial phase. So let us go with the data, so you will be getting more idea. So with the pressure buildup test also, we can get the effect of boundary effect. You can see that the point started to deviate. So moreover, we will see with data in the Excel, so it will be easier to get it. Pressure drawdown test. So this is the pink color data is built up. and blue color data is for drawdown. So this is for drawdown test. So we can get the value of permeability also. Let us see first of all what are the graphs that we are going to generate. So we are going to generate three graphs. One is this, and this. So first of all, drawdown, we need to know wellbore storage effect, transient flow effect, and pseudo steady state flow. You can see wellbore storage effect, transient effect, and pseudo steady. For that, we need PWF versus logarithmic time scale. So PWF value was here and logarithmic time scale. So I selected x-axis as well as y-axis. I'm inserting like this. Yes. So this is the equation that we got. I'm adjusting the axis value from 0 to 3000 is enough. And x-axis is logarithm. So you can see how the pattern have changed. And I'm going to take this to, I can use this axis to keep on one end like this. I'm going to remove the graph adjustments. You can see the graph was observed like this. So just what I want from here, what is that we can get? We will try to get the information. So the points have been deviated lower. The slope of these points starts somewhere around here. So that can be adjusted with inserting a scale. So you can see some points have been deviated at initial phase, some points have been deviated at final phase. So this is the part where you can observe that there is starting of boundary effect. Like, the pressure disturbance from the wellbore have reached to boundary. So up to here, you can consider it as transient period. After that, you can consider it as pseudo steady state flow. So we can this is the point where they started to skip from the starting point. This is one period, and this is the point where it started to observe boundary effect. So the period before blue line, I will change the color of this. Yellow. Yeah. So you have area before blue, in between blue and yellow, and after yellow. So after yellow is your pseudo steady state flow. In between this period is your transient flow period. And the starting period is your skin and wellbore damage effect. So this is the three phases that we can identify. I will just name all these three. This is skin and wellbore damage region. This is transient flow period. And finally, This is pseudo steady state flow. So these are the three different regions that we can observe. According to that, time also can be, say, for 1 hour, 10 hours. So in between around, you can consider from 1 to 10, like 5 to 6 hours, you will start to see the end of skin and wellbore damage, where the point started to fall on the slope. From there onwards, the transient period have been started. Then finally, the point started to deviate from the slope that represents the end of transient flow period at around 100, probably 400 or 500. It will be ending 500 hours. Then after that, you can start observing pseudo steady state flow period. So these are all important values, important parameters that we need to estimate during well testing process. Each Currently, I am just giving you the names of it, but I am not explaining what is pseudo, what is the steady state flow. Why? Because since I am going with application part, I am just getting. I mean, just going with application directly. I'm estimating the values of it. But if you know the significance of understanding these parameters through reservoir engineering, where we will be defining all the things that we are discussing over here, then you will be getting a fair idea on what is the significance of estimating skin wellbore damage, how it will impact the production, and why transient what happens in transient flow period. During transient flow period, what are the limitations, that and all we are supposed to get these values. Like, we should understand all this. Then only the well testing is like next to reservoir engineering. Like in reservoir engineering, we'll be talking the definitions and what are the significance of all these things. But when it comes to well testing, it's all about applications. Like you need to get the data, generate data. Well test is all about data. Like, you have to create the best patterned data. Like, you have to observe the patterns, you have to see the observations, you need to get data from different tests actually. Like, so in reservoir engineering, we are going to define each and every parameter. So when it comes to well testing, directly we will start estimating these things. Probably, understanding how these things can be estimated with simple data. Like, you have data, with that data, how many things you can able to extract. You may have little data, but you can extract a lot of things from it. You know what is a fracture, you where exactly fracture started, how to estimate skin, how to estimate probability, what is tortivity effect. Like that, there are a number of parameters are there that can be estimated in well testing. So uh, I started with this estimating with applications. I'm going with application part. But if you find it little confusing, please go through the definitions of what we have gone through up to now. Then definitely IPR we have done, GPR we have done, TPR we have done hydraulic fracturing, we have done right now pressure drawdown and build up. So I spoke about skin, I spoke about something, but these are all like through application where I'm just speaking it. But if you go deeply into the definition part of it, if you understand the conceptual part of that one, then definitely right now we are estimating these things. But yes, well testing will help you. Imagine you have huge data, you can generate huge number of value. Like, this is like data analysis. Like, you are going to understand what exactly is happening inside reservoir through well testing. But the definitions of what are there inside the reservoir, that is coming through reservoir engineering. So this is about pressure drawdown test. So we have similarly to conduct a pressure buildup also, and we need to estimate the value of permeability by estimating the value of slope. So this, to get the value of slope, we have a formula function is there, and we need to consider only few points, not every point which was deviated from the straight line. So you can avoid initial up to 4 points, 1, 2, 3, 4. So these 4 points at initial phase and the last 3 points, 1, 2, 3.
So we can start keeping here. So last 3 points you can avoid and first 4 points you can avoid. So let me keep this down. So this is the data I took. So first 3 points I'm avoiding and the last 2 points I'm avoiding. Sorry, first 4 points I'm avoiding and the last 3 points I'm avoiding to estimate slope. So in Excel, we have a function called slope, SLOPE. So in that way, it is asking you known y's and known x-axis. So known y's it is asking. First of all, y-axis represents PWF, but y-axis is linear, but x-axis is logarithm. It is a semi-log graph. So y-axis, nothing, directly take the values after 4 points, 1, 2, 3, 4. Since we are avoiding first 4 points, it is related to skin effect, 1, 2, 3, skin and wellbore effect, 1, 2, 3, 4. So after 4 points, select all the points, go down, finally you reach the point. Here also we are avoiding 3 points. So this is your y-axis. Then after that, just put comma and it is asking known x-axis. Directly don't go for the selection of it since it is your x-axis is logarithm. So you need to add log of your x-axis. So that also how many points you have taken for y, that many you have to take it for x. So it should not be impaired. So that means uh, the dimension should be same. So with that, you will be getting the value of slope. So 161 from 0.49 is my slope. So y-axis I have selected, x-axis I have selected, I got the value of slope. So I will use the slope value to get the value of permeability. So that is, I already have reservoir data a little, that is here. Flow rate, barrels per day, viscosity, centipoise, formation volume factor, barrels per STV, and hedges thickness 25 feet. So let us get this values over here. So my already formula is here 162.6 162.6 into Q value, that is flow rate, into viscosity, that is 3 centipoise, into formation volume factor B by slope value M value, which represents this value, into thickness 25. So I got the permeability as 45.3. So the value of permeability is in millidarcy. So I have the value of permeability as 45.3. I got it. I got the value of permeability as 45.3 millidarcy. This is what exactly we can generate. Not only that, the number of parameters with the help of permeability, you can generate skin factor also. So based on that, the process will continue to get the best outcomes through this data. Okay, let us go with the next topic. I think I'm already done with the time. And so pressure drawdown. Quickly, I will go into pressure derivative. And this is also a very advanced area in weight testing. So we have a derivative function. You can see the build-up test was over here. So this is actually build-up test and this is derivative function of it. So currently I'm not just giving you the formula to get these values. Through the course you can get it. So when you have a derivative function which you are interpolating exactly on your build-up test, you can observe so many things. Here C decrease, C increase, C or S decrease, C or S increase, S increase or K decrease, S decrease or K increase. So nothing but C represents wellbore damage effect. We have discussed about wellbore damage effect. So if the derivative function moves on this side, then wellbore damage effect is the arrow represents the direction of your pressure derivative function. So if it is moving towards right side, then the wellbore damage effect is increasing. Towards left side, it is decreasing. Decreasing is the one which is favorable condition to us. So increasing is the one which we doesn't need. I mean, this is not an ideal function for production. So in the same way, you can see a hump, like, it looks like a hump that represents
the time of your wellbore damage effect. So if the hump goes down, then C or S decreases. C, S corresponding the same like damage. So C represents wellbore damage, S represents skin, that also damage. So both damages will increase if the hump moves down. If the hump moves up, then the damage is increasing. So we want that damage to reduce so that the hump has to move. So more and more hump towards your build-up graph, that means there is more and more damage. In the same way, if the build-up graph is moving to top, then S and K, like S increases, K decreases. S and K are inversely proportional. Like imagine if skin is more, permeability will be less. If permeability is more, skin is less. So you can see S increases, K decreases. Obviously, the skin is the one which will damage the flow around your wellbore, so permeability will reduce. So if the graph moves towards top direction, then permeability is reducing and skin factor is increasing. On the vice versa towards opposite side. If the graph is moving down, then the skin factor is reducing. If skin is reducing, obviously permeability will increase. So currently it is moving towards top. That means S is increasing and K is decreasing. So this is the one, like, the pressure, this is for pressure build-up test, but this is pressure derivative function. Here hump we have seen. Then next to that, if the continuation slope, if it is going downside, then permeability is increasing. If it is topside, permeability is reducing. So not only that, we will be getting even more information like pseudo steady state flow. You can see that the graph, you can see the hump wellbore damage. See, it has written as wellbore storage hump. After that, it has taken a slope, a linear slope that affects a radial flow mechanism. After that, it started to, if it is moving to top, if it is a drawdown curve, if it is moving to top, then that is the indication of the reservoir have reached to pseudo steady state flow. This is for top, this is for down for build-up test. So drawdown and build-up test both has to be seen on the same scale. If the drawdown graph is moving to top, means that indicates pseudo steady state flow. On the opposite side, buildup is going down, means that indicates pseudo steady state flow. So this both will indicate pseudo steady state flow. But when it comes to steady state flow, not only buildup, even drawdown also will follow the same path. But that is the difference over from here and here. Drawdown moving to top, drawdown moving to down. But buildup on both sides are same. So with build-up graph, you cannot identify the difference between pseudo steady state as well as steady state. But drawdown is the one which is acting in two different ways. So this is the reason why drawdown is important for pseudo steady state flow measurement when it is compared to build-up test. Okay, there are some more functions which will have a lot of information about pressure derivative test also. I think my time was over. Thank you very much, and hope I will be